Good morning, everyone. I thank you for your time this morning. So what I do is I'll give a little quiz, all right? And I'm going to do that this morning. And I know what you're thinking, oh my God, I got to take an exam. All right, this is what we're going to do. Work with me, all right? I'm going to throw out a set of terms, right? If you are familiar with the term, just raise your hand, all right? Just raise your hand. And that'll, you'll see where this goes. All right, let's start with the term Clovis. How many of you are familiar with Clovis? All right, good deal. Clovis Point. If I had a Clovis Point, oh, all right. Pleistocene, megafauna. You guys, you're lying. I know, you guys are lying. Just like my students, right? Okay, all right. And then I know this Younger Dryas, Younger Dryas, you guys, everybody's here. They go, all right. Well, I don't know why I'm up here then, right? Okay, so everybody gets extra credit. All right, that's the first thing out of the way. The second thing, let me mention as a professor, I'm a professor of anthropology. I teach mostly archaeology classes, including North American archaeology. I consider myself I'm a mainstream archaeologist, and so to that extent, I'm probably somewhat in the minority here. I hope that when I'm done, you can come away with a little bit of an understanding about what we do in traditional, conventional archaeology, how we recover our evidence, the nature of what that evidence is, and most importantly, how we interpret evidence out of the archaeological record. Let me give you a roadmap, a brief overview, what I'm going to talk about. Those terms we just went over, that's a big clue, right? But so I'm going to talk about Clovis. I'm going to define the term Clovis as a continental-wide archaeological phenomenon. As such, I'll give you some dates on Clovis and its environmental context during the Pleistocene. The geographic extent. Clovis is a continental-wide phenomenon. We have manifestations of that right here in North Carolina, which will be really the focus of my talk. I'll talk a little bit about the sites and Clovis as a technology. That's what we dig up as archaeologists. And then I'll move right into how Clovis is manifested right here in North Carolina. That's been a focus of a lot of my research over the past few decades. I'll talk about the North Carolina Clovis Point. A North Carolina Clovis Point is a dead ringer for a Clovis Point in North Dakota, right? It's a continental-wide phenomenon with a couple of significant differences. Stone sourcing plays an important role in our understanding of Clovis in that not all stone was created equal with respect to its usefulness as a raw material. I'll talk about the spatial distributions of Clovis. This is really interesting. Some work I've been doing with some colleagues about what is the spread of Clovis in North Carolina. And then some exciting new study led by by Chris Moore. Chris mentioned Chris Moore earlier. Chris Moore is my former student at ECU, and he was the lead researcher on some blood protein residue analysis. You can get blood from a stone. And then the Younger Dryas, of course. And so Clovis is associated with the Younger Dryas period. I'm going to talk about the Younger Dryas. What is the evidence for the Younger Dryas proxies that we have in North Carolina based upon some sites I've been excavating along the Tar River in the eastern part of the state? Clovis. Clovis is an archaeological culture defined by a distinctive set of artifacts, particularly what we call a fluted point. It was first defined in the West, Clovis, New Mexico, for which it gets its name, back in the 1930s. The distinctive Clovis point you see there on the right, it's a lancelet-shaped point. Its diagnostic characteristic is a flute. A flute is a groove. Let me make sure I get, okay, see this groove, this flake that extends from the base of the point a quarter to a third of the length the way up. Now, what is that? What does it do? It presumably has some functional usefulness. The conventional explanations is that flute is on both sides of the point, by the way. That flute thins the base to facilitate hafting, right? This point was hafted on the end of a small spear. That's the conventional interpretation. Some interesting new research, however, suggests that flute may act as something like a shock absorber. That is, some experiments have been done replicating fluted points, replicating a point without a flute and then the point with a flute. And this research has suggested that points without a flute break more often on impact than points with a flute. That's maybe an interesting new functional interpretation of a flute. Clovis has a particular time range. It's defined, it's only about 300 years in length, from about 13,050 to about 12,750 years ago. It has been dated, about 32 dates come from 10 sites. And these dates, these sites are listed here, right? The dates come in these bars that you see here, these horizontal bars. These Clovis sites have been dated by radiocarbon dating. And I'll make a note here. Carbon dating, what you get is a statistical date. And so you'll get a date with a plus or minus factor of a few decades, maybe a century. So this is what's called the fudge factor. This is like, this same kind of statistical analysis is done in political polls, right? In case you didn't know, this was an election year, right? And so you'll see in polls, they'll say candidate A has 50%, is running at 50%. But there's always a plus or minus here of, say, 2%. What that means is that it could be 50%, it could be as low as 48, or as high as 52, right? And so that's what that interval represents, and that's what this statistical, this bar here, these bars represent. And interestingly, they sort of overlap, and that's good in that it helps define the 3 centuries that Clovis is currently dated at. Now, this is called the short chronology. We don't know if we really have dated the earliest Clovis date, right? And so I wouldn't be surprised if Clovis was actually a century or 2 earlier in the end, but we'll see. A couple of other things to point out here. Younger Dryas, you see that yellow bar there, right? Younger Dryas is this cold snap that occurs. I'll say more about that in a minute. But the Younger Dryas falls at the end of the Clovis period, right? If Clovis is roughly 12,800, right? And so the Younger Dryas is 12.8 or 12.9. So that's an interesting co-occurrence that I'll say more about. The other interesting pattern here is that this red line, if you can see in the back, that says megafauna extinction, right? A lot of big critters went extinct at the end of Clovis here. So Clovis occurs at a time in prehistory when there's a lot of interesting things happening in North America. Clovis occurs during the Pleistocene epoch, right? Pleistocene is a geological term. Clovis is an archaeological one. The common term for Pleistocene, of course, is the Great Ice Age. Why is it called the Ice Age? Well, because much of North America was covered in these ice sheets that in some places were 2 miles thick, right? All right. Hence the term Great Ice Age. Although it's called the Ice Age, temperatures in North America were not necessarily freezing all the time. In fact, some recent research has indicated that at the height of the last glacier, say 20,000 years ago, the average annual temperature was 46 degrees Fahrenheit. Cold, but not unbearably cold. But that's still a significant difference in terms of the annual temperature today. That 46 degrees is 11 degrees cooler on average than the average temperature in the 20th century globally, right? So that's a big difference. I'll point out one thing. This is a geological chart to the Great Ice Age, 2.6 million years ago until 11,700 years ago. That 11.7 is the beginning of the Holocene geologically. We are in the Holocene. Modern climatic conditions, modern sea levels, modern plant and animal communities, right? That's important. It shouldn't be surprising that if there was a great ice age 20,000 years ago, that the plant and animal communities that existed during that time were very different than exist today. And that's what we see in the Ice Age. In fact, this is called a non-analog, that the plant and animal communities that existed during the Ice Age were unlike any mix of plant and animal communities that we see today. There's no modern counterpoints for that, right? And so, for example, this picture here, you see the usual suspects for the megafauna, mastodon, the longhorn bison, saber-toothed cat, this interesting species of short-faced bear, right? All these critters went extinct in North America there at the end of the last ice age, some of which were hunted by humans during the Clovis period. So I mentioned Clovis was defined from work in the Southwest. Most of this was initially done as a result of kill sites where Clovis artifacts were found associated with the remains of extinct megafauna like mammoth. We have relatively few habitation sites. Living sites are usually not directly associated with the kill sites. And here in the east of the Mississippi, kill sites are very rare. That's probably a preservation factor, right? And what is more commonly found are Clovis points, isolated Clovis points found commonly on the surface of plowed fields, right? And so that is sort of the archaeological context that I've been working with. I mentioned that Clovis was a continental-wide phenomenon, and Clovis points have been mapped. This is David Anderson's work from the Paleo-Indian Database of the Americas. You can go online and see this. And what he has done, working with colleagues all across the country, have mapped the number of Clovis points per county. So what you see are these dots here. Whoops. Got to get see these dots, right? And so these dots that are mapped across the country. And so there's an interesting pattern here in that the points west of the Mississippi are smaller and more dispersed than the dots east of the Mississippi, right? You see how there's a lot more yellow and they're all much more clustered together than they are west of the Mississippi. Well, that's an interesting pattern, I think, that needs explanation. Now, some scholars have suggested that what it means is that Clovis settlement was probably denser in the east than the west, maybe. Some scholars even suggest that the greater number of Clovis points east of the Mississippi suggests that Clovis originated in the east. Well, maybe so. Whatever this interpretation represents, I think we can say there's Clovis lifeways have a lot of similar characteristics. One is that these folk were hunters and gatherers, right? They hunted wild game, they gathered wild plant food. This was the millennia before the presence of any kind of agriculture, domesticated plants in North America. As such, they probably lived in small family groups, what anthropologists term bands, right, moving about the landscape. Here we're using some ethnographic analogy from documented ethnographic hunters and gatherer groups like the Kalahari Bushmen, the Australian Aborigines. We're using that as kind of the model for recognizing the social organization of these of Clovis. As such, they were highly mobile. They had to position themselves. Hunters and gatherers can't live in one spot year-round. Why is that? Because they'd eat themselves out of house and home, right? And so hunters and gatherers have to move about the landscape to position themselves strategically on the landscape to exploit resources, particular resources, where and when they become available. And that's undoubtedly an important characteristic of Clovis lifeways. And given this mobility, I think one of the patterns we're seeing in all these dots on the map is two phases of movement. One may be a passing through, and the other is a settling in settlement strategy. Clovis probably represents the earliest widespread evidence of peoples in North America, right? I know there's I know what some of you think, well, there's pre-Clovis sites out there. Yeah, okay, but that's another lecture. You got to take my North American archaeology class for that one, right? We can certainly agree that Clovis is the earliest widespread evidence that covers the continent. And so we have people moving in, exploring a virgin territory. Think about that, right? These were some of the first people to set foot in North America, exploring the lower 48, and eventually then settling in particular regions and ultimately becoming some of the Native American groups that we know of today. All right, I said Clovis is a continental-wide phenomena, and we can see that in terms of the Clovis Point map, but we can also see that in the points themselves. A Clovis Point in North Carolina is often a dead ringer for a Clovis Point in North Dakota, right? Very similar technology. That flute we talked about, these flutes coming up from the base, these are fluted points from the southwestern U.S., and these are fluted points in North Carolina, right? And so the size and shape are very similar. The main difference in fluted points continentally wide is the stone from which they were made. And that's because the geological stone that was used to make Clovis points varies regionally, right? And Clovis folk used stone from the region in which they were inhabiting to make their Clovis points. So out west, you have a variety of chert outcrops that were exploited. Here in North Carolina, we don't have chert, but what we do have is a metavolcanic stone called rhyolite, right? And I'll say more about that in a minute. That stone type is an important evidence, a signature that we use to enhance our understanding of Clovis lifeways. All right, so I've been documenting the presence of fluted points in North Carolina since I was a graduate student at Chapel Hill back in the Pleistocene, right? Okay, and so I've been recording these. Most of these exist in private collections, right? Some institutional, but you got to get out and work with the amateurs, the collectors who are out in the fields, and so I've been doing that. So to date, I've documented 375 fluted points. I should note that 266 are Clovis. The other, the remaining number are, they're fluted, but they're a little bit different. They're stylistically, we refer to those as Redstone and Cumberland. I don't have time to go into detail about those, but suffice it to say, these probably post-date Clovis. They follow on the heels of Clovis in North Carolina. I've been publishing on this now for a while. That's some of the references for some of the papers I've written on this. Some with some colleagues, Al Goodyear, Chris Moore, in South Carolina. But we're now working, even as we speak. I'm working with my colleagues on a kind of a summary culmination paper on Clovis in North Carolina. So what I'm telling you this morning is I'm not going to say hot off the press because it ain't published yet. It's before hot off the press, right? You're getting the latest and greatest news about this. All right, so one of the interesting parts of the analysis is the spatial distribution of Clovis points in North Carolina. And this is a map here, obviously, of the counties. The number, the red number, represents the number of Clovis points in a particular county. And what you see here, there's an interesting pattern here. It's that Clovis points are found in about 70 of the 100 counties in North Carolina. 100 counties makes percentage calculations pretty easy, by the way, right? And so, but they're not evenly distributed, right? The average number is probably less than 3 single digits, but there's interestingly enough, there are some counties with double-digit numbers. You can see those here. Harnett, Wake, Granville counties, right along the eastern part of the Piedmont near the fall line. I think those are not by chance. And in fact, if you kind of just look at the whole distribution in general, right, you see that there are gaps and clusters in this distribution, right? And so you've got these main concentrations sort of the eastern part of the Piedmont. Then in the coastal plain, these numbers drop off quite dramatically. In fact, most of the outer coastal plain are counties with no Clovis points in them. There's also a gap on the western Piedmont. It's hard to see here because of the colors of the points, but there's a gap here, and then the numbers begin to pick up in the Appalachians here in the western part of the state. Now, I think this pattern is meaningful. That said, you got to be careful of biases in your data, right? Can you take this data at face value? There's probably collector biases, there's land exposure biases. We go over all this in the paper, right? But suffice it to say, I think there's something real going on here. And so we looked at this statistically, and so that's one of the things we have to do, you know, to kind of verify our interpretations. I can look at this and I say, oh, I see this clustering and stuff, and then people say, my colleagues go, oh, okay, well, I don't see that. Well, you got to back up these interpretations. One of the ways we do this is we do this with a simple statistical test called chi-square. Now, don't pull out your cell phones, and when I start talking statistics, the students kind of go, "Oh God, here we go!" Right? So just bear with me. This will be painless, right? So that's what this chart down here is, right? And so I looked at counted the number of points per region: coastal plain, Piedmont, and mountains, right? So the Piedmont and coastal plain, respectively, contain 45% of the area of the state, and the final 10% makes the mountains, right? If I did my math right, that equals 100%, right? And so if these points were distributed randomly across the landscape, if Clovis folk were wandering aimlessly across the state, we would expect to see these points distributed proportionately across each of these regions, right? So that's pretty straightforward. You would expect that 45% of the Clovis points would fall in the Piedmont. You would expect a similar number in the coastal plain, and then a somewhat much less frequency in the mountains because it only has 10% of the region. You with me on this? All right. But that is not what you see. This last column is the number of points that you see. What we see is a greater than expected frequency, 136 points in the Piedmont. We see a much less number of points in the coastal plain, 89, and then we see a slightly greater than expected increase in the mountains, right? We run this chi-square test, and that uses these numbers here. That's what all this is down here, and I won't go into that. But this last number here is p-value. That's the probability, right? 0.01 chance that you would see this distribution, less than 0.01% chance that these numbers would occur by chance. In other words, there's a 99.9% chance there's something non-random about this. There's something meaningful. What is that meaningful? And that is, I think that there is a reality in terms of why these points are clustered in the Piedmont, and we can see this better. This is a GIS map, right? You familiar with GIS? So this interpolation is taking those numbers and creating these clusters. And not surprisingly, we see this, this yellow with this real hot spot here, this sort of yellow. These are the interpolation, the number of points represented for the colors. And so 0 to 1 is this green, right? The really high numbers is the white here, and this, I don't know what that is, tan, whatever. And so right here, that is, I think that's a meaningful concentration. So there's clusters and gaps. A cluster here, very little on the, in the outer coastal plain. There's this gap in the western Piedmont, and then it picks up again in the mountains, right? I think what this, why are all these points clustered in the Piedmont? And I think one answer to that is that because the Piedmont is the hot spot for the natural occurrence of a certain kind of tool stone that was used to make the Clovis toolkits. The Piedmont, particularly the eastern edge of the Piedmont, is known for the Uwharrie Mountains. The Uwharrie Mountains occur in Stanley, Montgomery, Randolph counties along the Uwharrie River, right? And all those mountains are capped with a very unique type of stone, metavolcanic stone that my geology colleagues call a meta-rhyodacite. I just call it rhyolite, and they roll their eyes when I kind of butcher it like that. But these mountains are capped with that stone. I'm very familiar with this region because as part of my dissertation research at Chapel Hill, I spent the better part of several winters working with the late Bob Butler, pictured right here. He's you'll have to forgive me, I'm challenged with these things right here. So this is the late Bob Butler. He's a hard rock geologist at UNC. He was very interested. He had intimate knowledge of the metavolcanic sources in the Uwharrie Mountains. And so we teamed together in terms of looking for places where this stone was quarried. And we mapped and geologically characterized over 24 quarries in the Uwharrie Mountains. Why is this stone so unique? Well, if you're making a stone tool, you need 3 qualities to make a good stone tool. And this rhyolite has these 3 qualities in spades. One, if you're going to make a tool to butcher an animal, to kill an animal, to chop down a tree, you need a stone that's hard, right? Well, you say, Randy, all stone is hard. Yeah, okay, all stone is hard, right? But it can't be too hard, right? If it's too brittle, right? Some stone can be brittle. You can spend time making a stone tool, but then if it breaks, it snaps the first time you use it. What good is that, right? Well, rhyolite here is hard. It's not brittle, but it's the 3rd quality that separates this stone from all other stone in the state, in that it has a conchoidal fracture. That's a geological characteristic of stone, conchoidal fracture. What is that? Conchoidal means shell-like, right? And all that means is if you know where to hit a stone, if you know how hard to hit a stone, that you can predictably remove flakes to end up with the point that you want to make, right? So are you familiar with how stone tools are made, right? Have you seen those videos where you take a piece of, you got this chunk of stone, and you take a hammer stone or an antler, and you hammer the stone, right? It's a real skill, right? And so you have to know where to hit it, the angle, and so forth. But skilled flint knappers can take a chunk of stone, take a magic marker, and draw a little line on there, hit it, and they remove a flake that shape and size, right? And that's what Clovis folk were. They were extremely skilled flint knappers. Their lives depended on this, right? And so this stone, that conchoidal fracture separates this from all other stones in North Carolina, just about. Now, this is a LiDAR image. Chris earlier mentioned LiDAR, and so these white caps here, these little white caps from Stanley County up to Randolph County is the really hot spot. If you were a Clovis inhabitant in North Carolina 13,000 years ago, you knew where the Uwharrie Mountains were, right? This is where you went to retool, to gas up. And there's some really spectacular quarries, but I have to mention it's the most spectacular quarry is Morrow Mountain itself. This is Morrow Mountain looking from the Yadkin River, right? Morrow Mountain State Park. Anybody ever been to Morrow Mountain State Park? All right, good, good, good. This is your homework, right? When you're going to look at that Carolina Bay Chris mentioned, right? When you're driving around, when you leave this weekend, you got to go back to Stanley County, right? And go to Morrow Mountain State Park. You can drive up to the pinnacle of the mountain. There's a parking lot. Bring your lunch because you want to go to the picnic tables, right, from the parking lot. You cannot walk from the parking lot to the picnic tables without stepping on artifacts. I'm going to repeat that. You cannot walk without stepping on artifacts. People don't realize it, but what they're stepping on is the flaking debris from thousands of years of quarrying by prehistoric people. That's what you see here, right? See that gray? Those are all flakes. They're artifacts. This is an erosional ditch on the side of the mountain. All that sort of gray there, it's not dirt. Those are flakes. Those are flakes. So do yourself a favor, right? Visit Morrow Mountain State Park. Clovis folk did, right? And this is obviously this is a Clovis point made of Morrow Mountain rhyolite. If I was a betting man, I think this stone came from Morrow Mountain. All right, so not surprisingly, if you look at the raw materials of Clovis points in North Carolina, almost 50% of these of Clovis points are made from metavolcanic stone, this rhyolite, right? The next close is only 18% in chert, right? So this, to my mind, this kind of reflects the significance of these stone sources in North Carolina and why we see so much concentration of Clovis points in the eastern Piedmont. Now, I'm trying to focus on North Carolina, but of course, state boundaries meant nothing to Clovis folk 13,000 years ago, right? Right? That's obvious. And in fact, what we see is that Clovis metavolcanic points don't stop at the North and South Carolina border. They extend deep into South Carolina. Working with my colleague Al Goodyear, we've synced our databases, right? A Clovis point of metavolcanic stone that I record is probably the same metavolcanic stone point, a Clovis point that Al's seeing in South Carolina. And what we see here, this is another GIS map. We've removed all the other noise and focused on the metavolcanic points. And you can see this is that concentration. This is the North and South Carolina border. And here, metavolcanic points extend down to the watery Santee River in South Carolina. And you rarely see any metavolcanic points across the watery Santee River drainage. What you do see are Clovis points made of chert. Chert's a very different type of stone formed under very different sedimentary processes. Metavolcanic is a metamorphosed volcanic rock. Very different stone, very different stone. And so in the southern part of South Carolina, these are Clovis points made of chert, probably from the Allendale sources of Allendale County, South Carolina, along the Savannah River, right? Interesting then, you have Clovis points moving further south from the Uwharrie Mountains than you have Allendale chert points moving north. What's up with that? Well, I think what we're seeing here is that this distribution of Clovis points in the North Carolina here, that's mapping the territorial range of a Clovis band or bands some 13,000 years ago. In other words, think about, the trail of breadcrumbs, right? We talk about. So Clovis Point were making and using, losing, discarding, breaking Clovis points as they were moving about the landscape, like breadcrumbs, right? And each of those points, taken together, can map movement on the landscape. Remember, Clovis, by definition, these hunter-gatherers are mobile, and we have evidence, ethnographically of hunter-gatherers moving great distance, sometimes 100 miles or more. And so this is our interpretation of this kind of map. So Al affectionately calls the Allendale, the Clovis points, the Allendale Band. I call ours the Uwharrie Band. All right, so that's sort of Clovis. I mentioned the Younger Dryas, right? And so I want to touch on that a minute. The Younger Dryas is interesting. Remember I'll get it here. Remember that the Younger Dryas, the end of Clovis kind of marks the onset of the Younger Dryas, right? So what is the Younger Dryas? It's this cold period, this cold snap that occurred at the end of the Ice Age. Right? So at the end of the Ice Age, you've got the glaciers beginning to melt. Temperatures are warming significantly, right? After 14,000, 15,000 years ago. That's what this is a Greenland ice core data. And you can see this red line represents temperature. And you can see these temperatures are increasing dramatically, right? This is temperature this way. The bottom horizontal is time. And you can see after 15,000 years ago, temperatures are increasing dramatically. And then all of a sudden, say 14,000 years ago or so, then it starts to drop. And it drops even very dramatically, 12.8, 12.9. That's that little bar here, Younger Dryas. This temperature, that's degrees Celsius, but if you do that in Fahrenheit, it's about 38 degrees drop in temperature, right? And what's more, some scholars think this dramatic decrease in temperatures happened dramatically, like in a decade or less. What's the significance of that? That would have been within the lifetime of any one individual, right? And so people living there at the Younger Dryas would have noticed, hey, somebody flipped the switch. Somebody left the freezer door open, right? It's cold. It wasn't this cold last year, right? So this is an interesting occurrence that coincides with the end of Clovis, right? Oh, where does that name, odd name, Younger Dryas, where does that come from? Dryas is the flower, right? Dryas is a rare example. This is a genus name for an 8-petaled kind of white flower that blooms in the Arctic, right? You don't see too many flowers blooming in the Arctic, right? So it's a rare example of that was found. Pollen from the Dryas flower was found in a relative abundance in the Greenland ice cores at that 13,000-year period, right? And so there's a younger, what's the younger come from? Well, there's an older Dryas period that precedes it by sort of 1,000 years, and it was then interrupted by the Bowling Alarod and then the Younger Dryas, all right? All right, so somebody flipped the light switch. Why? How did that happen, right? And so there's several causes that have been proposed, right? I'll just briefly touch on these. You're probably most familiar with the proposed cosmic impact, right? That probably created this, what's called an impact winter, right? That maybe blocked the sun for significant periods of time, causing that decrease in temperature. There's also been a proposal about the shutdown of the North Atlantic currents, the thermohaline circulation. You know, there's, I'm not an oceanographer here, so bear with me. There's surface and deep water currents in the Atlantic, and there's a pattern all across the world, right? Some of those bring warm water, right, around. And so some have proposed that the melting of the glaciers at the end of the Ice Age caused this great pulse of fresh water into the North Atlantic that screwed up this circulation to the degree that it cooled the Earth. Right? One other similar explanation is it wasn't the melting of the glaciers, but increased rainfall that occurred at the end of the Ice Age that put a bunch of fresh water into the ocean that disrupted currents as well. And just one other last one is a volcanic eruption that created this, a similar kind of phenomena with this winter impact. All right? All right, so those are kind of the competing ideas with respect to the cause of the Younger Dryas. All right, I also mentioned that the Younger Dryas is also associated with the extinction of the megafauna, right? And so megafauna are the usual suspects. You've got mammoth or mastodon, giant sloth, camel, horse, bison, about 35 genera. Genera is the taxonomic name of a family that can include more than one species. So there may be several dozen species, 100 or more species that went extinct at the end of the Ice Age, right? Some of these were hunted by humans, right? Now, the question is, what happened? So you've got Clovis hunters, maybe an ET impact, you got all these animals dying out. Is there some pattern here? Well, again, there's several proposed explanations for the Pleistocene extinctions. One of these is called overkill. This was proposed by Paul Martin in the 1960s. He essentially said that these animals were overhunted by humans. Given that humans were fanning out over the continent 13,000 years ago, they found all these critters who had not developed any defensive mechanisms. These critters looked at this little two-legged thing running around, right, and they didn't figure out they should be scared of it, right? That two-legged critter had a spear with a stone tip on the end of it, right? And so Paul Martin's idea was that the Clovis hunters literally overhunted many of the megafauna, and that was a primary cause of extinction. Another plausible explanation is just climate change. So you remember, you saw that kind of dip in the graph, that warm, cold, warm again. Some scholars suggest that change in climate was so rapid that particularly these big critters could not adapt to that, and essentially that was the cause of their demise, right? Now, I should point out that these two explanations are not mutually exclusive, right? And some scholars suggest that working together, climate change and hunting were the mechanisms that resulted in the demise of the megafauna. And then, of course, we have the Younger Dryas impact, right? That is proposed that this is a natural, climate change is a natural phenomena, and the Younger Dryas impact is a natural phenomenon. It caused climate change too, right? But this is climate change on steroids, right? The Younger Dryas is, right? And if you're looking for a succinct statement about the Younger Dryas, this comes from some researchers in South America. They just published on this, and I'll read it. I'll paraphrase it for those of you in the back. This is your elevator speech, right, for the Younger Dryas, right? This event consisted of a major cosmic episode of multiple airburst impacts that occurred in North and South America, Europe, and Western Asia about 12,800 years ago. These impacts triggered extensive biomass burning, brief winter and climate change, and contributed to the extinction of the late Pleistocene megafauna. There in a couple sentences is kind of your take-home message for the Younger Dryas impact. But that begs the question, were megafauna actually hunted in the Carolinas, right? We have no, here east of the Mississippi, preservation is such that we don't find preserved remains of animals in the same way that you find them out west, right? And so we're desperately looking for a kill site, but that, particularly in the Carolinas, those have yet to be found. But we have found some other direct evidence of human and megafauna interaction that, again, by Chris Moore, was the lead author on this project. He collaborated with us, collecting Clovis points and some post-Clovis points in the Carolinas and conducting what's called a blood protein residue analysis on these. And we found blood protein residue of what we believe are extinct animals like mammoth, bison, right, and horse. This was published in this paper in 2017 in Scientific Reports. So, very briefly, I'm not an immunologist here, but how can blood protein be preserved? Well, this is a technique that is a method. This is a method used in forensic, right? This is CSI stuff, right? It's been used for several decades in criminal investigation to identify unknown blood spatters, right? We're just now been done to try and see if blood protein residue can be preserved on stone tools. How is it preserved? This blood protein appears to be preserved in the microfractures in stone, right? If I talked earlier about how these stones are flaked, right? That flaking process in the edge of the stone creates little fractures, little tiny fractures. And I think it's intuitively understandable that if you're taking this stone point and piercing an animal, butchering an animal, there's a lot of blood in that, right? That blood is on the stone, it gets absorbed in the stone, and can be preserved for millennia. It involves the process to extract this, to determine what it is, involves the same kind of antigen and antibody process that is found in the body's natural defense system. Antigen, some bacteria, an antibody to fight that bacteria. That's the kind of the process used in terms of identifying the blood protein residue in a stone tool. So they're adhering to these artifacts. The blood protein residue acts as the antigens when tested against antisera, the antibody, right, from known animals. So we're taking antisera from known animals, right, and trying to match it with the blood protein residue off the stone tool. And so we use living animals. Now, we don't have any living mammoths, right, to get that, but we do have some elephants, right, and so we have bison, we have species of animals that are in the same kind of family that we're using to be the background comparative benchmark for these. And so very briefly, how does this work? You take your Clovis point, put it in a solution, a chemical solution that with an ultrasonic bath, that releases the residue out into the solution, right? A sample of that solution is taken out. It's put into a gel substrate with the antisera. They are electrically charged. That's the electrophoresis part, right? Immunoelectrophoresis. It's charged over about a 45-minute period. Then the blood protein residue begins to migrate toward that antiserum, and if there's a match, if there's a positive match, then it ends up producing this kind of line. Damn, Randy. All right, it produces this line right here, right? That's a positive match, right? And that tells us that there is a match, at least at sort of general family level, right? So our results, we used 120 artifacts in North and South Carolina. We only got a positive hit on 18 of those, only 15%. That's a low return rate, right? But we're talking about 13,000-year-old blood protein, right? So it's a wonder any of this is preserved, right? So the moral of the story here is you need big sample sizes here, right? And we're working on reproducing this with additional samples of artifacts. The positive results were interesting in that we got positive results on Clovis Point for proboscidean. Proboscidean is the sort of family for elephants, right? Proboscidean, we got positive for bovid or bison, and equid for horse, right? All those are for Clovis, and some extant species like deer, right? But what is particularly interesting is that we had some post-Clovis points, redstone points. They tested positive for bovid and equid for horse and bison, but there was no proboscidean. That's an interest. Is that real, or is that sort of chance, right? Does that mean, so what is the implication for this for the megafaunal extinction? Well, it's hard to draw much in the way of real conclusions, but the fact that we're not getting a positive hit on those post-Clovis points for proboscidean is kind of a tantalizing evidence about maybe, the elephants died out at the end of the Clovis era, whereas horse and bison lived on. I don't know. Stay tuned. We're going to do some more work with that. All right. Finally here, I know I'm wrapping up my time here. Finally, I want to talk about some of the Younger Dryas impact proxies that we found along the Tar River, right? We've got no Clovis sites, unfortunately, but we do have, I think, proxies that suggest the Younger Dryas impact that is consistent with Younger Dryas impact that elsewhere, that Chris Moore. My student, Chris Moore, worked early on in his tenure as a graduate student. Chris helped in some of the excavations. I should have never let Chris graduated, right? He did. I got more work done with him as my graduate student than I did when he left. All right. So, but what are you going to do, right? What are you going to do? So the Tar River, eastern North Carolina, a major river drainage, and so I wanted to set out and do some archaeology on some sites there that I believe to exist along the Tar River. This is, again, a LiDAR map showing that we did a series for over a decade, virtually every summer for over a decade, we did survey and testing at these sites. And these dots here, right, represent about 19 sites. Chris used LiDAR images. What we were looking for is geological features, these relic sand dunes in which we had reason to believe stratified archaeological sites were preserved. These relic sand dunes, as the term implies, are all these deep sand built up over millennia, probably started forming about 15,000 years ago, wind-blown sand with some flood deposits, creating these sand ridges. They ceased to form around 3,000 years ago. And that's what these images here, the two sites in particular I'll draw your attention to, Barber Creek down here in Pitt County, Squires Ridge up here in Edgecombe County. That's where we did the most extensive excavations and where we found evidence of these proxies. And so we looked for these ridges, these sand ridges on LiDAR. You can sit at a computer and sail up the Tar River looking for these geological features. And then we had to go ground truth them to make sure there was archaeology in them. And that's what this ridge here, that's a relic sand dune. That's Squires Ridge. A similar one is here, Barber Creek, right? And so, as I said, we started this work in 2000. The last shovel was was excavated in 2012, virtually every summer. As part of the ECU, we have an annual archaeological field school where our students learn in a hands-on fashion. Yeah, how do you learn archaeology? Well, we have these armchair archaeology classes. I teach a methods class. I call it armchair archaeology. For the students who are really serious, you got to get out and pick up a shovel and trowel, right? You got to get dirt under your fingernails. And so that's what we do every summer for training for our archaeology students. So this is examples of some of those trench excavations we did at a variety of these sites. Now, and what we find, there were stratified remains. The earliest occupations we got were early archaic, about 11,000 years. No Clovis. There may or may not be reasons for that, but I can go into that later if you want. But what we did find good early, middle, and late archaic and early woodland occupations in good stratified context. And so those are typically represented by the early archaic, these notched points, corner notch points in the lower levels, stemmed middle and late archaic points in the upper levels, and then in the very most upper levels, just below the ground surface, we get the woodland component, the hallmark of which is pottery. Pottery comes in late in prehistory, and that's what these portions of reconstructed vessels you see here, these sherds. I had students sit in the lab doing these jigsaw puzzles with pottery, right? And then, of course, those vessels are associated with these small triangular, these are true arrowheads, right? These are more like spear or dart points. Lastly, these are end scrapers. These are scrapers, and if you were paying attention, that stone there should look familiar, right? If I was a betting man, I think that stone came from Morrow Mountain along the Yadkin River and traveled from the Yadkin River to the Tar River, right? Right? That's pretty. I got so excited the day I found that. The students were going, "What the hell is he doing?" I say, "You don't understand. You don't understand where this came from." So, but I get excited about little pieces of rock, right? Okay, so we got the stratified type, but we also have chronometric dates. We've got radiocarbon dates and OSL dates. Radiocarbon is you date charcoal, right? That's I obsess over little bits of charcoal, hickory nut shell charcoal, that come from levels of our excavation associated with those artifacts. We also have OSL dates, optically stimulated luminescence. Sand grains can be dated, right? It's amazing the advances in technology, right? Hell, they're getting Neanderthal DNA from dirt in caves in Croatia, right? Right? So why should we be surprised by being able to date sand, right? And so this profile, briefly, the profiles on the right here, this is Squires Ridge, this is Barber Creek, stylized profiles showing the similarities to the sand dune. You've got dates here. This is about 14,500 years ago right here. That's probably the base of the dune when the dune started forming, right? Then you've got other dates that are progressively younger. And then we also have radiocarbon dates from organic remains that are consistent with the OSL dates. This is an early occupation surface right here, a bunch of busted up flakes. These are 3 cobbles that were busted up in this little 3 or 4 foot square, right? And these can be refitted, right? If you don't get excited about that, then you don't need to be in archaeology, right? Somebody sat there 10,000 years ago and busted up a few cobbles, right? When I see that, I know why I'm an archaeologist, right? All right, up a little bit higher, about 40 centimeters, we have remains of a stone. I think the remains of a stone hearth. Right here. That's about 5,500 years ago, those radiocarbon dates. And then at the very top, the woodland dates about 4,500 years ago, 4,400 years ago. Frankly, that's a little early for me. I'd like that date to be more like 3,000, but maybe the early woodland was that early. I mean, that's why we do this, right, to find out what the real deal is. So I love this saying down here, all right, to find old sites, you got to find old dirt. Well, we got plenty of old dirt along the Tar River. So I said we don't have any Clovis, but we got the Younger Dryas proxies, and there's a whole list of proxies. Chris touched on some of those. The 2 main proxies that we found along the Tar River are magnetic microspherules, right? And so this is an example of a microspherule from Barber Creek right here. These microspherules, you have to use a scanning electron microscope to see these. These are spherules that are formed presumably from heat and pressure that could probably caused by some kind of impact. They're often found great distances from the initial impact. These were found in sites, about a dozen or so sites all across North America, including the couple we have here in North Carolina. There's also nanodiamonds. That's what's pictured on the right here. Nanodiamonds, how small is a nanodiamond? It's pretty damn small, right? So these are formed also under heat and pressure, presumably as a result of some kind of impact, right? Platinum anomalies. I'll show you a graph of the platinum anomalies. This may be kind of there's no smoking gun here, right? No one of these is considered a drop dead kind of fingerprint, right, of a cosmic impact. But if you put them together as a group and they're coming out at the same level, at the same age, I think an impact is the best working hypothesis we have, the most parsimonious explanation to explain the co-occurrence of these, right? And then the last one I'll just mention is this soot, these wildfire, the impact winter, right? In some places we see these soot in abundance, right? Much greater abundance than earlier or later in the level. So for our purposes along the Tar River, the microspherules and platinum anomaly. And so this again, Chris Moore, this is a paper published in 2017 where he laid out the initial evidence for this, the microspherules from a number of sites, including the red box there outlines the two sites I've been working on, Barber Creek and Squires Ridge. And this column here on the left is just kind of a blow-up of the figure on the right. All you got is sand, right? All you got is sand. It's hard to see much in the stratigraphy. That's why we dig by level and we piece plot all these things. But we're taking out organic remains and OSL samples up and down the column. In addition, we're taking out soil samples that are then analyzed for various signatures, including the spherules and the anomaly. And I'll just point out this big spike here. That's a platinum anomaly. This other blue, there's platinum, but it's lower levels. This is a real spike, right? This is consistent with these spikes across these other sites, right? All right. So this, to me, again, this is an impact is the most parsimonious explanation I have for this clustering of materials, right? All right. So let's bring this home. Clovis in North Carolina, looking at fluted point surveys, looking at these private collections, that's our best way to gather evidence for Clovis occupation until we find that Clovis component buried somewhere, right? There's methodological advances being made in this immunological studies to get blood from a stone. How exciting is that? Stratified sites with Clovis-age sediments do exist in the coastal plain with these YD proxies, and continued effort needs to be done to locate an in situ Clovis component in North Carolina and document the presence of these Younger Dryas chronostratigraphic marker in the coastal plain. So this is sort of what I think of as mainstream archaeology. We have our story to tell too, and North Carolina is a big part of that story. Thank you very much.